Okay, in this final slide here, or in this final tape rather, I would just like to go through a couple of problems. And as before, what you should do is you should pause the video right here and try to work the problem yourself without my help. But then I will go through it and you can compare your answer with mine. Okay, so it takes 5 steps to convert ethylbenzene into the nitrile shown here. And how would we go about synthesizing this? First, you should think about how many reactions have you had during this semester that incorporate the cyanide group into an organic molecule. And there's only one. It's in Chapter 8. It's our old friend, the SN2 reaction. So, as the final step here, the most logical step is to treat a tosylate. You could use a halide or something like that as well with sodium cyanide, and that would produce the final product. Okay, so where does the tosylate come from? Tosylates always come from alcohols. So this is our immediate precursor right here, this alcohol. Okay. We can't just magically plop in an OH group at that carbon. There's got to be some trick to it. We know the last 2 steps here. It must take 3 steps. Let's think about how do we make primary alcohols. Well, the solution there is in Chapter 6. You do the hydroboration of an alkene. The anti-Markovnikov hydration using the boron reagent will get you there. And now you're starting to see some resemblance between this intermediate and the starting material. Okay, all we have to do is introduce a double bond where none existed. Okay, so our way that we're going to do this, our second to last step is most likely going to be the elimination step, because we can add bromine, or we can replace a CH bond with a carbon-bromine bond, but we don't know any reactions in the class that replace a CH bond with a CO bond. Okay, so this is the most logical step, and of course this last step involves the treatment of the starting material with NBS and light. Okay, let's look at some alternate ways we could have made this as well. Let's see. Let me see if I can get this to come here. Okay, I'm trying to get the pointer options here, so I want it to be a pen. Okay, so what are some alternate ways that we could do this reaction here? Well, it's possible to treat this with PBr3. I'll just draw the resonance hybrid here. Get the bromide, and then treat this with NaCN. It would also be possible as well to treat it with SOCl2 and get a chloride. Okay, so that would be an okay way to go as well. Okay, let's look at another problem here. Write a mechanism for the following transformation. If you treat this alkene, or this triene with bromine, you get a rearrangement, and it produces the aromatic ring shown there, NHBr. Let's think also, in addition to what is the mechanism, why does this reaction go the way it does? Okay, let me just offer you a hint here. I may not need to offer you this hint, but I think I will anyway. This is the initial site of the reaction right here, okay? That double bond, and you can kind of tell that is where you're going to have to start your reaction because of where the bromine is in the final product. And remember, this is a mechanism problem. We're going to have to use bromine to get here, nothing else. Okay, we're not going to have any OH minus or anything like that. We're just going to have to use Br2 as the only reagent that's going to transform that starting material into that product. Okay, so let's just imagine this is a chapter 6 problem. We're going to start this reaction by doing the electrophilic addition of bromine to the double bond. Okay? Now, once you have the carbocation here, of course, this is a resonance stabilized carbocation, right? Okay, so this is a resonance stabilized carbocation. We can draw a resonance structure that we draw for any allylic carbocation. The resonance structure shown here. Okay, at this point, you can now see a reason to do the the shift of the alkyl group. So the shift of the alkyl group produces the compound there, and once this compound is made, of course, we're just going to lose the bromine, or lose the extra hydrogen rather, and that's going to give us the product. And of course the driving force for this reaction is the fact that the product is aromatic and the starting material is not aromatic. Okay? And this is the reason this reaction goes this way, is why you don't just simply add bromine across the double bond or do a 1,4 addition. The fact that you form a benzene ring makes this reaction go via a different reaction pathway. Okay, let's look at this one. We're going to show the steps in the formation of the indicated products. And here I'm going to tell you what the mechanism is. You just have to show what the steps are. The steps are 2 Diels-Alder reactions. One involving the starting material, and one is a retro-Diels-Alder reaction involving the ejection of carbon dioxide. And I'm also asking you to tell me what the thermodynamic driving force for this reaction is. Okay, before we even look at the mechanism, we can tell what the obvious thermodynamic driving force for this reaction is. We've got a lot more benzene rings in the products than we do in the starting materials. So the formation of the benzene rings is the true driving force of this reaction. Okay, so let's look at how this starts. It starts out as a Diels-Alder reaction. And here's our Diels-Alder reaction. Okay, that electron deficient alkyne reacts with that diene to make the product shown here. This is a pretty good Diels-Alder reaction because it makes a benzene ring where no benzene ring existed before. Okay? So that's a pretty good reaction. And by doing a retro-Diels-Alder reaction here, and I'll just show it with the arrows in the retro-Diels-Alder reaction here, you generate another benzene ring. Actually, my arrows aren't that good. I'm not drawing the actual benzene ring. Let me redraw that here, because that one's not that great. Okay, so what we want to draw is we want to draw it on this side. Okay. All right. Okay, same set of arrows basically, except I draw them on this side. And now you can see how carbon dioxide is made. There's also, in this last step, not only do you form 2 benzene rings, but it's also entropically very favored because it generates, you get 2 molecules from 1 molecule. So this is in the disorder in the universe increases as a result of doing this reaction. So this reaction is quite favorable. Okay, this will be the last problem that we do, but let's see if we can address this one. Which carbocation is more stable and why? Of course, if this were on the exam, most of the credit would come from the why, because you have a 50% chance of getting this one correct just by guessing and not knowing anything about carbocations. Okay, so let's see this one. Is it the one on the left or is it the one on the right? Both of them are pretty good carbocations. They're benzylic carbocations, but how is this methyl group's position influencing the relative stability of these carbocations? Well, it turns out the one on the right is more stable, and it's more stable due to resonance. Okay, let's look at how the resonance plays out here. Alright, so the top one is here. Alright, so here's the top one. Or, the left one. We can draw a series of resonance structures that we would write for any allylic carbocation. But notice that never in any of the resonance structures we write do we ever have a case where the carbocation and the methyl group are right beside each other. Just focus on these two, where you basically take the position of the carbocation and you totally more or less bypass the methyl group. Now if you look down here at the bottom, of course, when you start drawing this resonance form here, you generate a really good tertiary allylic carbocation, and this is especially good. So in the one on the right, okay, methyl group is stabilizing the carbocation. Whereas in the one on the left, the methyl group is not really contributing very much to the stability of the carbocation. Okay, I think this is the last of the shows here. Let me just say, I hope everyone does okay on their test, and good luck and have a happy Thanksgiving break. Okay, and I think that will be all of the tapes here for Chapter 11. Okay. Discard. Alright, so I think that's it.